So here I've selected a random location. Now we will see what happens when we change the latitude. So as I increase the latitude, it moved towards north, and as I decrease it, it is moving towards south. Similarly, for longitude, if I increase it, it's moving towards right, and if I decrease it, so it's moving towards left. So accordingly, we can use these values. So let's start the code. So here I've divided the code in 4 tabs so that we can read it better. So let's start. In the first 2 lines, I've declared 4 objects of servo type, channel 1, 2, 3, and 4. So what this basically does, it will be used to feed the values from Arduino Nano to KK Flight Controller. Next, we need to read the 6 channel inputs from the radio receiver. So we are using some variables just for that, which will be used to read the 6 channel outputs from the receiver. Next, we have some declarations for the compass. Here we are using QMC5883l compass module. So accordingly, we are using this library, and here we have declared an object of the same QMC. Okay, next, the declarations for GPS module. I'm using tiny GPS++ library for that, and here are some declarations. So with this, our declarations are over. Now let's move on to the setup part. Okay, so first, let me tell you, the GPS by default starts at 9600 baud rate, and the location is updated at a refresh rate of 1 Hz by default. But this is too low for our drone. So let's in this part, what we do, we just change the baud rate from 1 Hz to 5 Hz. So first we have to start it at 9600 baud rate. Next, we just disable some messages, unwanted messages, using the uBlocks protocol. Next, we change the refresh rate to 5 Hz. Refresh rate to 5 Hz, as you can see over here. I also commented the same. Finally, we change the baud rate to 57.6 kbps. And next, restart the serial communication to 57.6 kbps. With this, we have successfully changed the refresh rate from 1 Hz to 5 Hz. Okay, here I have declared one pin output. We will just connect a LED to this pin, which will be used later on to indicate that that the GPS location is updated. Okay, so here we are using 6 pin change interrupts, 4 at port C, 4 at port C, and 2 at port B, in order to read the 6 channel outputs from the radio receiver. So here we didn't use A4 and A5 of port C because those two were already busy with the SCL and SDA for I2C communication with the compass module. So we have used two ports, so two pin change interrupts of port C. Okay, so next the compass part. Over here we are just initializing it, and finally we are setting the output of the four channels: aileron, elevation, throttle, and yaw to the default starting values. So next, let's see the interrupt service routine. So we will be basically using two interrupt service routine. One for port C, that is PC int 1 vector. This will take care of channel 1, 2, channel 3, and channel 4. Okay, and we have another interrupt service routine for PinChangeInterrupt 0 vector. This will take care of channel 5 and channel 6. Yeah. So let's just see one of this. Let's see this block and we will understand how exactly this is working. So as soon as this interrupt service routine starts, we are initializing the current count reading in microseconds. Next, since the channel outputs are PWM values, we will read the duration for which a pulse is on or off, and that will basically give us the required value. So here, if the last channel state was 0, we will change it to 1 and initialize the counter 1 value to current count. And if this is 1, we set it to 0 and update the channel 1 output to the difference of current count minus counter 1 value. So basically, using this, we will be getting the duration for which a pulse is on. That is what we need. So if the pulse is on for 1200 microseconds, so channel 1 output will give 1200. So this value can be in between 1000 to 2000. So all this are done similarly. Now let's move on to the loop. Okay, inside void loop, first we are reading the 4 channel outputs. For the throttle or channel 3 output, we are mapping it in between 1000 to 2000 since we have some problem in reading the lower value. We're not really getting 1000 when the stick is at the lowest most position, so we are just mapping it accordingly. Next, we need to set the P latitude and P longitude values. So for that, we are using channel 6 output. So this using channel 6 output, we can vary the P val in between 0 to 10, and accordingly we will change the P latitude and P longitude values. So next, whenever this part is for the GPS, okay, so whenever we are getting any serial data and the GPS location is updated, first we change the state of this LED. So this will basically indicate that we are receiving and updating the date location data. And as soon as I start getting the signal, this LED is glowing. Okay, as you can see. So as soon as the location data is updated, we save the previous locations and update the current locations. As simple as that. Finally, using channel 5 output, we are changing the mode. So for case 0, we are operating at normal mode. So here we are just updating the initial compass value. And one thing is important, make sure that the front is facing towards north for GPS hold feature to work. Our algorithm assumes that our front of the drone is facing towards north. Next, we just update the latitude and longitude positions. Okay, so for in case 1, what we are doing, we are enabling yaw hold mode or direction hold mode. So we are calculating yaw change based on the current compass value and the initial compass value that we read in case 0 or 0 mode. So using that, we are calculating the yaw change and augmenting this yaw change value, or simply adding the yaw change value to the final 4 output. And once again, we are just setting the initial latitude and longitude with the current latitude and longitude. Finally, in second or third mode, we are enabling GPS hold mode. So the first part is the same. We are ensuring that the drone is facing towards north, like the front is facing towards the north. Next, what we are doing, we are calculating the alignment change and elevation change values based on the P latitude and longitude values. P latitude and longitude values. PD controller, simple PD controller has been implemented over here, and this is just the difference between the required position and the current position. While this is basically the current longitude value minus the previous longitude value that we got. So this will basically give us the speed at which the position is changing. So this part is basically giving air is working like an air resistance kind of thing. So next we are just limiting the alignment change and elevation change values so that we will still have control over the overall sticks, so that we will just still have control. Finally, we just add these two values, and outside the switch case, we just write these values to the respective channels. With this, our code is done.